This talk is on using TMS as a tool for neuroscience. There's 3 talks on TMS, I believe. I think I'm giving the first one. Holly Lisenby will be talking most likely on how to use TMS in psychiatry. It's a method that's been approved by the FDA for treatment of depression already, and it's actually useful for, maybe useful for OCD and schizophrenia, in stroke. It was first used in the late 80s, 1980s and early 90s, by neurologists actually before psychiatrists got a hold of it. And the last people to get a hold of it were people like me who are experimental psychologists. I find it a very, very useful tool. I started out using brain imaging. I started using MEG, and then PET, and then MRI, and EEG. And the problem with all of them is they're very nice, but just lighting up the brain or looking at activity related to some behavior or some task, for instance, is all correlation. It's not causation. Here, I can actually stimulate the brain and affect it and do an actual experiment on somebody without hurting them. That was, to me, a very powerful and new and useful tool in experimental psychology. What I'd like to do a little bit of today is just kind of show you where we are with that and show you some ways that we've been able to look at network activity and to probe the brain in terms of brain behavior relationships. Okay, let's see. That one? Yep. Okay, so TMS comes under, transcranial magnetic stimulation comes under the heading of what we're sort of calling NIBS now, though it sounds kind of silly. But non-invasive brain stimulation, which at the moment is any kind of addition of energy. It's usually electromagnetic energy, either electric currents, like a thing called transcranial magnetic, or rather transcranial direct current stimulation or alternating current stimulation. There's magnetic stimulation, of course, which is what I'll be talking about. I just saw a few talks recently on using ultrasound, which allows you to very specifically go in areas in a 3D kind of way into the brain, and there's a lot of hope that that's going to be very interesting as well. Although to me that's like shaking neurons, I'm not quite sure how it works yet. So there's a lot of different ways of adding energy into the brain in a very specific way to affect it and see if you can work out what's happening causally. Okay. TMS itself, I should say what TMS is, which is, again, there's, like I said, I forgot to finish my original statement, which is there's 3 talks. Somebody walking in just kind of reminded me of that. And Holly Lisenby will talk about the psychiatry end of it, and Z Deng and Tom Radman, who are also in our unit, will talk about the basic physics of TMS. So I'm not going to talk a lot about that either, except just to say that you're just inducing, with TMS, you have a very, very rapidly changing magnetic field, and you're inducing currents in the brain due to that magnetic field that are proportional to the amount of magnetic field that you're actually, and the change in the magnetic field that you're actually producing. The change can be up to 2 Tesla. Okay, at the surface of the coil that we use right next to the head. Geometry is everything, distance is everything in TMS. You can only go a few centimeters deep effectively in terms of creating things like action potentials. There's a lot of calculating and physics and stuff involved with that, and again, I won't be talking about that. We're just going to assume that it magically produces currents in the brain where you put the coil. The rest you'll have to go to another lecture for. The effects that TMS causes are multiplying quite a bit lately. There are effects that happen immediately, such as action potentials. So you have a very fast, rapidly rising and then decaying magnetic pulse. And like I said, they're up to 2 Tesla at the surface of the coil. And so very large and sort of on the order of what you see with MRI. And these produce very small currents in the brain. One of the very first experiments ever done, I gotta use the right mouse here. Okay, this is my pointer. Okay, come back. There you are. All right, by Vahi Amassi, and this is in 1989. So TMS actually started around 1984, the first machines, and this is one of the very first, what I'd call brain behavior psychological experiments done with it, which is that Vahi Amassi showed people 3 letters. They were very hard to see in and of themselves, but you could. They were only on for about 14 milliseconds, but nonetheless, most people. This is 3 different people. The tracing the curves of 3 different people. When Vahi did a single pulse, okay, at a certain time relative to when he showed those 3 letters, when he did the pulse, and this is the occipital cortex, when he did the pulse immediately. Nothing happened. Okay, people still saw the 3 letters. When he did them at about 80 milliseconds or so, or 100 milliseconds, suddenly people couldn't see the letters anymore. Okay, and that's because you're basically injecting an awful lot of noise in the form of random action potentials into occipital cortex at the very time when we know that that's when the information gets to, well, it actually can get there earlier, but when V1 is doing its processing of pattern information, such as the letters and identifying the letters. So there's actually, there was a window of when he could stimulate that would affect the ability to see the letters and process the letters. So this was a first demonstration of the use of TMS to actively change a given area at a certain time or at a certain location. Right? That gives us the ability to deduce what's going on in that area. Okay. And again, a very powerful tool. This is one of the first things we saw. We got very excited about it. I and Ali Lisenbeek and a few others started doing this in 1995 at Columbia, and then at Duke, and then finally here. Some of the best and earliest TMS work that was done actually by the NINDS right here at the NIH in Building 10. At any rate, so there are acute effects, and they can happen for a very short period of time. You can see that it's stimulating a little bit later didn't do anything, okay, in this particular case. There was, for instance, about a 40 millisecond time period where you could affect processing going on in this area with a single pulse. So that's a direct activation of various brain circuitry. That allows you, for instance, I wrote motor twitch here because if you stimulate motor area, you can make various muscles contract, and that's one of the ways we actually dose how much TMS we give people and try to make it equal across individuals with a motor threshold. Okay, and by finding the smallest amount it takes to activate, a given cortical area. In this case, something we can see, like a twitch. Okay, and we actually measure that with EMG. And I keep pointing to the motor cortex when I talk about that. So at any rate, you can do some various things. You can disrupt speech. You can create phosphenes in visual areas, and actually. You can actually see disruption, for instance, of motion in visual areas, and you can produce muscle effects as well. But about 80% of the brain, 80% of cortex, you can't really see the results of directly, and you have to do much more sophisticated experimentation to see anything. But these are things that only last just a little while, okay, on the order of milliseconds and seconds, all right? But there's multiple time scales here, because if you do more TMS, if you do trains of TMS, for instance, for 10 or 15 or 20 minutes, you can create effects that last another 10 or 15 or 20 minutes past the stimulation. Okay, so you can create a longer term effect. If you repeat TMS over and over again, day after day, and so here's an example. This is from the very large multi-site study that led to the approval of TMS in depression. And these are depression severity scores. You can see that after giving people TMS, 10 hertz, so 10 pulses a second, for 4 seconds on, 26 seconds off. You do that for 37 minutes. You do that every day for a week, and you repeat that week after week. You can see this is active versus sham TMS. There's a small difference after 1 week. After 2 weeks, rather, that difference grows by 4 weeks and is even bigger after 6 weeks. Okay, so 6 weeks is actually the FDA label for using TMS in depression. You see a long-term buildup, okay, a long-term change due to the fact that TMS has direct effects on mechanisms of neuroplasticity in the brain as well. So you have things that happen in milliseconds, tens of milliseconds, minutes, days and weeks and months, okay, using TMS. You have multiple time scales involved. I'm just going to put all this on there. And there are a huge number of parameters that we're just beginning to explore now with TMS. And so, for instance, with a single pulse, okay, that's a certain waveform. It's a dampened cosine, but it doesn't need to be. And there are now machines that have been built. Actually, we've worked with the people that designed and built them to create, for instance, instead of a dampened cosine, you can make a square wave. All right, square waves actually may be better to use. It depends how neurons interact with them, with the various waveforms that you create. You can make that longer or shorter. Hello, as well. Okay. So there's a lot of things you can do with the pulse itself. Then you can do trains of TMS. So then you have frequency of the TMS. You have time between the trains, the intertrain interval, the duration of the trains themselves. You have the intensity of the TMS pulse. And again, you have the number of pulses, number of trains, number of sessions. It even becomes more complicated, all these temporal parameters, because you can do pattern TMS. Okay, so this is a tiny little schematic right here of a thing called theta burst, where you actually stimulate a gamma frequency of the brain. So in this case, 50 hertz. So 3 quick pulses at 50 hertz, and you wait 200 milliseconds and do another small train of 50 hertz. So you're doing it at theta frequency, 5 hertz. So you're doing 2 different frequencies at once, and those nested frequencies actually may be much more potent than just single frequencies, for instance, trains of single frequencies. Then you have, over here, you have the kind of coil you use. We generally tend to use a figure-8 coil that tends to concentrate the magnetic field at the center of the coil. And again, you'll hear lots about coils at Zidang's and Tom Radman's lecture. You have different kinds of TMS devices. You have where you put the TMS. You have the orientation of the coil. That actually matters quite a bit. The direction of the current relative to a gyrus in the brain actually matters quite a bit. So there's a huge number of parameters involved. It's an infinite space. And like I said, we've just begun exploring it. It's a little tricky exploring it because to just explore it by yourself, I mean, it costs money. You need to get MRIs. You need to spend the time to do the TMS, et cetera. You need personnel. And so for that, in the outside world, you need grants. And most grants aren't given for people to just explore parameter spaces. So one thing is we're trying to do that here where we don't need grants. So that's a nice service that the NIH can do, for instance. So, for instance, I was just mentioning waveform itself. So this is a very typical monophasic waveform, all right, just going up and down with the current. You can actually do a biphasic, where you go up, down, okay. These are the standard waveforms often used by almost all the devices, but there's a new kind of controllable TMS device that lets you, for instance, make a square wave, okay, whether it's monophasic or biphasic. And we actually tried that a few years back. There's a very standard paradigm where you can give some pulses to motor cortex and just see, you'll get a motor evoked response when you do that with a single pulse, and you can just get about 25 of them or so and just get a kind of average size for that. And you can do some kind of stimulation to people. And one very standard one is to do it for 15 minutes, say at 1 hertz. 1 hertz will tend to lower cortical excitability. And actually what would happen is when you tested again with motor cortex, you will see that these pulses on average get smaller. Okay? You've kind of created sort of an inhibitory effect on them. Really, you've down-regulated cortical excitability, if you want to say it in a longer phrase. And so what we did was on individuals, we tried on different days various waveforms to see what would happen when we looked pre and post. And what's expected when you do 1 hertz for 15 minutes, like I said, is that you should see a decrease in amplitude. But that's kind of on average over a whole group, and it happens in about 2/3 of people. Okay, so if you get the wrong 2/3, if you get the wrong group of people, we only use 13 people in this case, you may not even see an effect, and that is in fact what happened. I lost it again. Anybody see it? Where is... Whoa. Oh, there it is. This is the standard waveform. Here is baseline, so we just kind of normalize relative to baseline the amplitude of these motor evoked potentials, or MEPs, and you actually don't get an inhibitory effect, okay, with the standard waveform, in this particular case, with this particular group, with this paradigm, and yet using square waves, we did. Right, and it lasted a little while and then wore off. But we actually saw that using a square wave was more potent. Okay, for instance, so just the way we shape the wave matters quite a bit in terms of the responses of the neurons to the TMS. So again, just starting to explore that, but we're finding much more potent ways to use TMS as we go, and it's going to be a better. And the whole point of my talk, I hope, is that we're creating a tool that's much more precise, that can be used across individuals, and be able to know what's going to happen, predict what's going to happen in a much better way. Right now, it's more hit or miss than it should be. Another thing that was noticed very early on with TMS was frequency matters at the trains, for instance, with repetitive TMS. Higher frequencies above 3 hertz will upregulate cortical excitability. Low frequencies around 1 hertz downregulate it. Right? This is just an early PET, 2000 PET study with excitatory 20 hertz TMS that really, it sets off an action potential in a given place, and that spreads it throughout the brain. Okay, of course, inhibitory is not going to do that as much. You just see a little bit of inhibition or deactivation rather with that. And it turns out to be a much more complicated story, most likely. So, for instance, this was a study done in 2003 by Klimesh and his colleagues, where they had people just do a mental rotation task. The Shepard's got a very famous mental rotation task where you're basically asked, you're shown a complicated geometric object, and then you're shown another one, and the question is that the same one that you just saw rotated, or is it a different one? It's a little bit difficult to do, but you get the hang of it after a little bit. And when Klimesh gave TMS at an individual's peak alpha frequency, they recorded their alpha frequency and then gave the TMS at that frequency, he found that people, when he did that to either prefrontal or parietal area, he found that people increased their accuracy. If you gave just a train of peak alpha frequency TMS right before they had to do each trial, they actually increased their accuracy quite a bit, on the order of 12% with that stimulation. Oops. Whereas they did not with TMS that was given at 3 hertz less than their peak alpha frequency, or with 20 hertz TMS. So the point here is that how TMS interacts with ongoing cortical oscillations, which more and more we're realizing turn out to be quite functional, also really matters. And again, just barely being explored. Another interesting effect aspect of the fact that you're interacting with the brain when you do TMS. Okay, you're not just like operating on it and bringing things up and bringing things down, and that's it in terms of excitability, which some people tend to think of. Oh, it's a way of lesioning the brain, virtual lesion. It's nowhere near that simple. So, for instance, if you think about the brain, and you should, as a homeostatic organ. So I had just mentioned that 1 Hertz paradigm, where you look pre and post at MEPs, to motor cortex, and look for an inhibition if you do 1 Hertz for 10 or 15 minutes. And when people do that, you get this kind of function. Here's the pre-treatment. You get that inhibition, then it kind of goes back up again, and that's all very nice. On the same people, when 6 Hertz was applied, right before the 1 Hertz 10 minutes was done, a bunch of trains at 6 Hertz rather, this is what happened. You had a much more profound and long-lasting inhibitory effect, okay, on the MEPs. You really potentiated the effect. It is most likely due to the fact that that when you apply the 6 Hertz, okay, you're upregulating cortical excitability, okay. So, but your brain's fighting that. It wants to bring it back down again to this, whatever level that it was happy at. That's the homeostasis part. So, when I give the 1 Hertz TMS, okay, the brain's already in the process of bringing things back down, okay, from being upregulated. All right, now I'm adding something on that downregulates, so it's already itself downregulating, while I'm externally creating something that downregulates, and that most likely makes an overshoot, okay, and a potentiation of this downregulation. So there's a lot of ways we can work with the brain, okay, to create much more powerful effects with TMS as well. And again, just starting to be explored. Another interesting part, I mentioned theta burst before. I don't know what I'm touching over here. I mentioned theta burst before, which is those gamma trains, short gamma trains of say 3 pulses at say 50 Hertz, and separated by 200 milliseconds, so it's running at theta frequency. When you stimulate with that kind of pattern stimulation for 2 seconds, what am I touching? And then you wait 8 seconds, and then do it again, and do this for a couple of minutes. You potentiate, you upregulate cortical excitability, say in motor cortex. All right, and that's right here. So again, we're looking at pre and post, this theta burst with MEPs, just testing it out, and normalized against the baseline MEPs, you see that there's this long-lasting potentiation, okay, of effect. If all I do is run that pattern stimulation, that theta burst stimulation, I wasn't even touching it, continuously, all right, for a few minutes, you create the opposite effect. Right. So here's the continuous theta burst, and here's what happens when you do that. You actually downregulate it. Right. It's the same pattern stimulation, and all I did was put an intertrain interval in, between 2-second bursts of the TMS instead of running it continuously. Why does that happen? I don't know. Anybody here know? No. I don't know either, and it's something we're going to be looking at ourselves. But again, this kind of a dynamic that between TMS, how you're running the external stimulation with these various parameters and what's going on inside the brain really, really matters. Another thing, of course, obviously, the first thing people thought of is just being able to focally stimulate the brain, okay, stimulate a certain location in the brain. And the very first way we did that in any kind of systematic way is by using a 10-20 system with EEG. So there's electrode sites, and you can measure and go to those sites on each person. So it's a relative measure on each person, but it gets you over certain spots in the brain with a certain amount of precision. That was used in the beginning. We went on when we could bring MRI, for instance, into things. We can look at structural MRIs and use neuronavigation, okay, to more precisely find a place on the cortex to stimulate. And you can do that more functionally by using group coordinates, okay, from fMRI studies, for instance, of where, what part of cortex is activated in a given task, and aim at that particular cortex. And you can do better with that by doing that on an individual basis. So have people do a task in the scanner, find out what's lighting up and exactly where is lighting up in that person, and aim at that with neuronavigation. And so, again, with the 1020 system, with scalp-based systems, which, by the way, the FDA label, okay, for depression basically uses is scalp locations. The actual areas in the brain, this is from an earlier study. There's later studies that also have done this. I guess you can't see them, but there's little dots in here that represent where on the cortex a given electrode site ended up on an individual. And you can see that they kind of cover, every electrode site kind of covers a pretty large amount of ground in the brain. You don't know where on any individual you are if you just use a 1020 system, except you're kind of in this general region, all right? So you're on the order of a centimeter or two error in terms of resolution when you stimulate without, kind of blind to having a brain itself to look at. But now, and since the early 2000s, we've had neuronavigation. You can use an infrared system, and you can co-register a person's structural MRI or an fMRI overlay on that structural MRI to the person, in 3D space while you're in the TMS session. And you can keep it, and you can generally keep the coil, the center of the coil, right over a target that you pick on the brain. So that's a much better improvement. In fact, there was an experiment done a few years ago where they took 4 groups of 5 people. This is when you just, these people had a task that they used that they knew would where there's a TMS effect on it. I don't have to go into that at the moment, but when they stimulated parietal area, they did create an effect. And what they asked was, if I do a power analysis based on the results that I found, the behavioral results I found when I did TMS in these various targeting ways, how many people would I need to see my TMS effect, in a group basis on a 0.05 level, P of 0.05 level. And so you can see, for instance, that when they use the 1020 system and they use the electrode site P4, these are the 5 different brains for this group. That you can see it ended up, where they stimulated ended up in a bunch of different places. These are totally unrelated to what's going on in the brain. It's just whatever random relationship there is between the scalp and what cortex is underlying it. So there's a lot of variability that's just random and not functionally related. And when they actually do a power analysis, it turns out that you would need about 47 people to get a P of 0.05 level with the data that they had. If you use, these are for structural and group-based fMRI, and structural MRIs, just look at anatomical, that's a little better. And in fact, you needed about 10 and 13 people to get that effect. Now here you can see 5 people where the stimulation, you see it's also quite varied where you actually ended up. But this time you're stimulating at the center, of the activation, okay, due to the task. And when you do that, you need 5 people to see an effect of a significant effect on the task of TMS. So this was a kind of a nice example. The N is very small, but just a nice demonstration of the difference of these different targeting methods. And if you do TMS now, and so we generally don't do TMS unless we have imaging to use, and I wouldn't use TMS without that unless you're just doing motor cortex. And do TMS on an individual basis, you can do a much better job of actually localizing a spot and aiming for a functional area in the brain with the TMS. And you can even improve that even more because you can take, there's a lot of variability even with neuronavigation due to the fact you have a human operator trying to position the coil, and you have individual subjects who move, all right? When you're sitting there doing a task, you often move. what you can do, and so that creates a lot of spatial error. What you can do is use a robot, and we had that set up down at Duke when we were there and at Columbia. And the robot will actually follow, okay, that site and stay with it, no matter what the person does. It'll go to that site with 1 millimeter accuracy. And by the way, there's also with figure-8 coils, there's 3 degrees, okay, of wobbling that the coil can do, and it'll stay within 1 degree of wobble, all right, in each of those. Did you?
Just finished, then I've got a question about this functional equalization.
Okay. Where was I? Okay, 3 of wobble. So it'll have high resolution in all 6 parameters, spatial parameters of how the coil has to be adjusted. This really can increase accuracy as well.
So along these lines, so if you've got running a study, you're doing fMRI localization, and 8 of your 10 subjects are all nice, high on the brain, but then 2 of them, the major localization, the major functional attribute is falling like into the gyrus.
Yeah.
I presume that's going to have wild effects on whether or not TMS is going to affect it.
Yes, and I was just going to say something about that.
Okay, never mind. Sorry.
It's okay. And I don't have a slide on this at the moment, but there are ways. What you really want to do is actually calculate how much electric field you're actually inducing in your target area, no matter where it is, right? On some people it might be deeper, on some people it might be right on the surface, right? You never know exactly on any individual where it's going to be. You can actually calculate, how much field there should be, and know how much, what you should set the intensity at, and how you should orient your coil to get at that spot with the same amount of electric field. Okay, there's a whole.
Got it, and just pray that the cortex that you're passing through doesn't have an effect on the task.
Yes, so I try to leave religion out of it, but yes, the idea, yes, you can't do anything about that either. Is you're just hoping that what you're aiming at, because you're aiming in a certain area. You can aim with the center of the coil with millimeter precision, but it is affecting a square, 2 square centimeters, depending how deep you're thinking about, of neural tissue as well. So you're trying to put the biggest intensity exactly where you want it, and yeah, it does have effects around it too, and none of that's ever thought about too much. Okay. So and again, yes. So we're actually even working harder on actually getting exactly the dosage, okay, of electric field, at the spot you want it, in a way that's comparable across people. And that can make a big difference, we think, because where you actually want to stimulate, can be different and can be deeper. And like I said in the beginning, geometry is everything. So that may, and we're studying that as well right now. How much of an effect that actually has on things. So. Just in terms of targeting, we're able to really. I think, do a very good job in getting better at precisely stimulating, a given region in space. And by the way, one reason that we're kind of interested in ultrasound as well is that will just affect, whatever we're aiming at, and not the other tissue as much as at just the one area. But okay, having said all that about spatial targeting, not only are you affecting kind of the area around it as well, a little bit less, but still affecting it. Also, when you're creating action potentials, you're stimulating a network. You're not stimulating just one site, okay? And people tend to make that mistake, and we're trying to correct that when we talk about TMS. When you say you're stimulating, a given site, or you're affecting a given site, you're not. You're affecting that site and whatever else it's attached to, okay? You're affecting a network. And that's okay. The brain works in terms of networks anyway. But it's important to keep in mind, but one nice thing is we have tools to see what those networks are. So, for instance, and we have this here at the NIH in Building 10. We had it at Columbia, we had it at Duke. You can just buy off the shelf now machinery systems, TMS systems that will work in the scanner. Okay, so you can actually stimulate in the scanner. It's interleaved TMS fMRI. What you're doing is here's the fMRI pulse, and you can follow it by a TMS pulse because they're so short, okay, you can stick them in between the fMRI pulses. And you have enough time for the effect, the electrical effects, the various electrical effects of the TMS to kind of discharge, wear away before the next fMRI pulse. And so it's essentially, in a lot of ways, very not noisy, noise-free, something. The signal to noise is very good. We've done a number of studies with that kind of thing. This is not our study, but another group, for instance, you can look at long range effects of networks and TMS. So, for instance, here's a case where you're doing working memory task. You're shown a number of faces or a number of houses, for instance. Faces will affect a large number of places, but including the fusiform face area. And the houses will affect the parahippocampal face area, amongst other things. What these people were able to show, okay, this is Farados et al., was when they stimulated dorsal prefrontal cortex and looked at the activation levels, okay, of the fusiform face area or the parahippocampal place area, they didn't have any effect if they stimulated during the retention period before you're asked, did you see this face or not, before you're tested. And that's okay because probably dorsal prefrontal cortex isn't involved when you don't have to worry, there's no interference or anything. But what if there is interference in the task in the form of showing some objects in the intervening time period, in the retention period, before you're tested? So when they stimulated that way, when they're doing the face task, the activation of the fusiform face area increased. Okay. When they did the same situation when they're doing houses, when they're showing interfering stimuli, the place area, parahippocampal place area, increases intensity. And what you're able to show is long-range effects of what's going on in the prefrontal cortex with what's the kind of processing that's happening in the posterior cortex. I always thought this was a nice example. Another example that we did was, I've already said TMS kind of only goes a few centimeters deep. You can actually model that. So for instance, this is a simple model using a sphere. You can kind of see a brain in here. You can see that a figure-8 coil at the dosage level we often use, which is the 100% of the motor threshold. And you can see that basically action potentials are caused down to about here, okay? What if your target, for instance, is down here? And this is a target based on deep brain stimulation in depression. It's a subgenual area, Brodmann area 25. We'd like to stimulate that area, but you really can't get to it directly, just with a figure-8 coil. However, you can get at it transsynaptically. So, one idea is, can I go through one synapse and affect activity very, very deeply, and in my mind, anywhere in the brain. So what we did, that went the other way. What we did, there must be stuff on the side of this mouse. Well, what we did was we scanned people, did DTI on them, looked where the white matter tracks went out to their polar, the frontal pole, which we can reach with TMS, then we brought them in, put them in a scanner, stimulated the frontal pole area where they're, on an individual basis, where their particular white matter came out to, and at different intensity levels to see if we could affect this very deep target that we seeded for DTI. So we're stimulating out here. Can we affect this very deep area, and can we affect it in a dosage-dependent manner? So here's 10 people, and here's where here's on an individual basis where the white matter tracks came out. That's kind of the group average of the DTI. When we stimulated and we looked at area 25, we showed that we could, with increasing TMS intensity, we increased the activation of that area. Okay, so what we showed was that you can actually aim for very deep targets. You have to do it transsynaptically. A number of different groups are trying that out right now in terms of there are people going for the amygdala, for the hippocampus, for this area 25, to affect people in terms of substance abuse, in schizophrenia, and in depression. Those deep targets that are of interest to psychiatry. And it does seem to be working. And by the way, it's not just MRI imaging, and it also works for PET imaging too, but EEG. And what EEG gives you is temporal resolution. This is one of the very first times. It's very kind of hard to do TMS and EEG at the same time because the TMS pulse tends to swamp out, EEG amplifiers. But there are ways of dealing with that, and there you can buy systems now. We have one here at the NIH where you can actually do a high-density array of electrodes. If you stimulate, for instance, motor cortex, you can see the response to that stimulation at 3 milliseconds with EEG. You can see it spread to premotor areas and somatosensory areas in 10 milliseconds, in one synapse away. You can see it cross to the other side. In 24 milliseconds. You can do the same thing with an occipital stimulation, but you can actually make temporal maps, nice little movies if you want as well, of what's going on due to the TMS pulse across the brain. So you can look at a dynamic mapping of what happens with the TMS pulse with EEG and MRI, and now the big thing that people are trying to do, and we're actually going to do something similar, is can you do stimulation, MRI, fMRI, and EEG in the brain, in a scanner all at once. Okay, and that's the new thing to do, so you can actually get a spatiotemporal mapping of what's going on. Let me skip that because I'm running out of time. So I've said all that. All right, so just some examples. Here is a case that we looked at. Here's a task that somebody, Paul Scheide and his group at Columbia used, where, I'm afraid to touch this, where faces or cars are shown. You have to say, it's a two alternative force choice. Do you see a car or a face? And these are spatially degraded stimuli, and and you can actually degrade them at different levels. You can see, at a high level of coherence, you can see the face. As you basically degrade the image more and more, it gets less and less easy to see. Oops. Wait, I lost it. Okay. So that's the task. So you can make it as hard as you want. And one thing that they found out with a couple of EEG studies and then an MRI study is there are a number of EEG components that come out. There's one early on. There seems to be a middle one, and there seems to be a late one, here, on the order of 170 milliseconds, 225 milliseconds, and more than 300 milliseconds. And it turns out that later component has everything to do with actually trying to make a decision, is this a face or a car, under very difficult circumstances of trying to discriminate. And they were able to model it very nicely using diffusion models, random walk models. And what we asked, and how long, when that late component started, for instance, its latency, it increases latency when you increase the difficulty, and it also increased its duration. And as well, this middle component seemed to have a lot to do with this. So this seems to have a lot to do with the difficulty of the task, and very much related to the drift rate in the modeling, the diffusion modeling. So they were able to tie it to psychometric functions, the physiology of psychometric functions with this late component. If you stimulate with TMS, we made a prediction based on this. And this is nice. This is what you can do with TMS, for instance. If they do very good work relating the physiology to the psychology, the brain and behavior at once, you can start making predictions based on when you should stimulate, for instance. And if I stimulate in this late period, right? And what I can do is I can figure out a coherence level in people and have everybody at about the same level of difficulty, the same level of accuracy by titration methods, with the task and with various coherence levels. You can kind of equate people that way, and you can predict that at a given time, for a given window of time. Okay, we actually did 2 stimuli. We did paired pulses to kind of cover those windows that they found. If you stimulate at a certain time that I can force people into based on this modeling, then I should slow them down. I should slow the drift rate, for instance, of the decision making. And so we predicted that if we stimulated at 400 milliseconds after the stimulus came on, if people were operating at about a 77% level of accuracy on this task, that we would slow them down. We slow their reaction time down. So we actually made a prediction. And we knew where to stimulate too, because they did an fMRI study and found that the late component mostly had to do with the lateral occipital complex. Okay, so we stimulated either on the left or the right on people. We did one at a time on different days. This second component, so they have a nice spatiodynamic model. The first component seems to occur at 170 milliseconds. This one that has to do with difficulty seems to have mostly prefrontal areas that seem to be activated when you need them to help you with that difficult situation. And the processing to make the decision seems to be going on in lateral occipital complex. So if you stimulate lateral occipital complex at 400 milliseconds, we predicted that we would slow people down. And I'm not going to go through all this, but that's what we found. Okay, this is reaction time. Here's 400 milliseconds. Here is no TMS. Here is 500 milliseconds. So this late component is over at 500 milliseconds. We also wanted to kind of bracket that window and show that was true. And there's no difference between 500 and no TMS, 500 milliseconds. And when you compare 500 milliseconds with the 400 milliseconds, you can see that there's a slowing that happened due to the TMS. So we actually were able to predict something, and it worked. We found 2 more effects with this as well. We found that when we stimulated right before the stimulus came on, you actually got faster, okay? And you actually got more accurate, okay? We actually improve people at a certain latency. And that generally tends to be true when you stimulate in a task right before, when people have to, on a trial, when people have to do the task, you tend to, you can, with the right set of parameters, you can improve people's performance. And we've done a lot of that over time, and I may have time to show you some of that. We also found, we also stimulated at the time of, we bracketed that 225 milliseconds by stimulating 200 and 250, a paired pulse there, to see, because that difficulty component that peaked at 225 milliseconds had a lot to do, its amplitude, okay, was related to, for instance, the onset latency and duration of the late component. They were highly coupled with each other. When we stimulated at that, the peak time of that component, but we stimulated LOC, we didn't stimulate the other network, we actually created an effect on accuracy, a qualitatively different effect. We didn't affect reaction time at that time, but we affected people's ability, people's accuracy and discrimination, and really in terms of how well they were able to discriminate cars. And in fact, we could look at the different titration levels that we got for, how people, at an individual level, how people were able to discriminate cars and how well they were able to discriminate faces. People that could discriminate cars the best were the people that TMS affected the most. And there was a nice relationship there, only with stimulation at 200 milliseconds. So we were, able to show 2 different, one very highly specific prediction of behavioral effect in this network, or set of networks, I should say, and we were able to show some of the coupling, that we could affect some of the coupling of these 2 networks when the situation is difficult. So this is like a first attempt at exploring this particular set of networks for object discrimination, but you can actually do some very, very precise predictive work with TMS in this kind of exploration. So it's a very powerful tool that you can use, and it's causal. We're able to actually show LOC, at this time is doing perceptual decision making, or it's involved in that processing. And you can do a lot more, after that's a first step. I'm going to skip this. That's the performance enhancement. And by the way, that was an unplanned performance enhancement, which is what we always found in the beginning. Because we always thought TMS was disruptive. You're injecting a lot of neural noise, random neural noise in an area. That should be disruptive if the processing is ongoing, and that's true. So if I stimulate when processing is going on, I mess you up and you do worse. If I stimulate at a different time, I can actually make you better. We've published reviews on that showed that can happen because you can do disruption where you're knocking out another competing network that's not really useful in a task, and you can make people better in that sense. But you can also directly engage a network, which was what we were doing in this case. And there's a number of ways you can do that. But again, I'm not going to have enough time to go through that. So here's another experiment where we looked at, this is kind of a hot area right now, but the inferior frontal junction, or the IFJ, which Desimone, who was here a while before, when you stimulate the IFJ, that seems to have a lot to do with, for instance, visual search. Okay, it seems to have that top-down function on posterior areas that have to do with kind of trying to find objects, in a given field of distractors. We also, by the way, in this task took advantage of oscillatory activity like that Clemish study, which I mentioned previously. So we stimulated people's individual peak alpha levels. And these were the targets that we used. We tried to use something that was ecologically valid. And this was for the Air Force, so they had us looking for, on reconnaissance photos, various targets, like Scud missile, whatever. Fire offerers, what do you call that? Shooter offerers, Scud missile launchers. And these are really shooter offerers. These are really hard to see, and it takes a while to train people up on this task. But what the Air Force wanted us to do is, can we make people better at seeing, in these photos? Can we make them faster? Can we make them more accurate? And we said, give us money, and yes, you can. And so we used these targets, and the idea is people went to the target as soon as they found it, and so we're looking at reaction times. The accuracy is they have 4 seconds to find it. And so we would stimulate, again, we wouldn't stimulate, this is like the time when the target is on, the stimulus is on, and we stimulated at their peak alpha frequency for 5 seconds right before each trial. And we also were able to individually find a target site. So we stimulated 2 different targets, parietal area and the inferior frontal junction. Okay, this is a group mean, but we're able to find these targets. We looked for it. We know the general region where IFJ is anatomically. We found the greatest activation for each person, so we were targeting on an individual basis these 2 areas. And what we found was, for at least IFJ stimulation, this is active and this is sham, we're able to make people faster, okay, with that stimulation. So we were able to improve people, okay, we in a planned way, okay, by knowing the area. And in this case, we kind of guessed what frequency we should use. In normal TMS, what you want to do is you have to kind of do a little bit of work ahead of time to figure out parameters like what frequency do I use. This was some pilot work. That's a joke. Pilot work, reconnaissance photos. Never mind. Just thought of that. This was pilot work, so we had to make a quick guess, and that was our best guess. It may work at a better at a better frequency. So if I then got an R01 for this, what I would have done was, first looked across parametrically across a number of frequencies to find the best frequency. Okay, there's another aspect that I have 5 minutes to tell you about. Another aspect of targeting that actually improves things even more, which is functional targeting. What you want to do is have neurons that are involved with your task, okay, active, because plastic effects, neuroplastic effects, work better, and it's for Hebbian reasons. You want to get an area active, and then you want to do the external TMS stimulation. Okay, 1, 2. Okay, so those neurons they're firing together, so they wire together. Okay, so you want specific neurons in an area to be active, and you want the ones that are involved with your function, if that's what you're trying to affect and improve. The simplest way to show this kind of effect is by having, for instance, you can electrically stimulate the median nerve. You can do a stimulation. You can wait 23 milliseconds or 25 milliseconds for the stimulation to get to the brain. Okay, then you stimulate at the brain. So you can pair kind of an internal stimulation with, or affective stimulation with an external TMS stimulation. When you do a bunch of pairs of those, okay, and you look again in the motor cortex, and you look again at MEPs pre and post, you can see a big potentiation of the MEPs due to this pairing. Okay, this is called paired associate stimulation. And it's pretty well known now. It works pretty well. We've kind of generalized that into what we call CPAS, or cognitive paired association. So instead of just doing median nerve stimulation, I can use any kind of stimulation. So for instance, I can have people do a task. So I can stimulate people, and I can have them do the task. So if I try to do those things simultaneously, aiming for the area that's involved with the task, so I'm activating that area and I'm stimulating there, that potentiates effects of TMS. Right? So it's a way of trying to get control of the state of the brain, okay, which is very important nowadays. We're finding out TMS totally depends on what the state of the brain is, at the time you're stimulating. This is a kind of methodology we've been working on for the last 10 years or so, and in 3 minutes, just using, for instance, a Sternberg paradigm, okay, so a working memory paradigm where I show you letters, I wait a little bit, and I show you another letter, just like that faces in places thing I've shown you before, but with letters, is that letter the same or different from the one you just saw? It's a speeded reaction time task. It's a very nice one. It's got very nice properties to it. As you add letters, the encoding period, you add to the people's reaction time as they have to go through more. When we did our search, parameter search, first we tried to find places in the brain that get activated with this task. One is midline parietal cortex. Another one you can't see here is dorsal prefrontal cortex, because that's always activated with everything. And we simulated both of those. We stimulated at 1 hertz, 5 hertz, and 20 hertz. And these are 2 different set sizes that we were using. And what we found was 5 hertz, this is active in sham TMS, you were speeded up with active compared to sham TMS, okay, at 1 hertz and so set size 1 and at set size 6. And when we stimulate, this is when we stimulate during the retention period. When you stimulate during the test period, so we ran a whole nother group of subjects, and we replicated that effect during the retention period, that's here, where we speeded people up, but we did nothing to people when we stimulated during the probe period. Okay, so we actually showed, we're able to say, okay, what we want to do is stimulate at 5 hertz during the retention period at certain locations. Right? So very specific, and so once you do your homework, once you get that part done, you can actually try things out. And what we did was we made people worse at the task. Okay, we actually gave them a cognitive deficit in working memory, and we did it by having them stay up for 2 days. Okay, so they were sleep deprived, and when you're sleep deprived, you slow down. Okay, so the other thing that really happens is you kind of phase out. You have little micro sleeps, and you kind of miss tasks, so you have lapses. So just in terms of reaction time, when we found a network that was activated, that decreases activation in pre-post sleep deprivation, and it was sensitive to the task, namely across sleep deprivation. The more you got worse at the task, the bigger the deactivation was. So we stimulated essentially LOC, lateral occipital complex. We also stimulated right out of it, just a centimeter outside of it. and we stimulated that parietal area that the previous slide you saw was with people that were just wide awake, still speeded people up, and that was still part of that network. What we found was compared to sham, we did indeed speed people up when they were inside the network. When they were just right outside of it, we did nothing. You can see it's the same as compared to sham. And we speeded people up somewhat with that parietal stimulation. And the more that network expression decreased with people, the more TMS helped you. Okay, so we showed a nice brain behavior relationship with this as well. But this is an acute effect. Okay, what we want to do is can we create an effect that's long lasting? And I'm almost done if you give me a minute or two here. So what we did was we stimulated people. We did that functional targeting, our CPAS type paradigm, where where is it? There it is. We stimulated people at 5 hertz during retention period to LOC. Okay, but we did that during the 2 days of sleep deprivation, and we were giving them TMS while they're doing the task for an hour at a time, twice a day. Okay, so they got a lot of this TMS, at the same time. Okay, and we, multiple repetitions, which, as you remember from depression work, also works to create a long-lasting effect. And we tested them a full day later. Okay, no TMS. They're still sleep deprived now, and we asked, how are they doing behaviorally? Well, when people were not sleep deprived, they basically, if you're below 0 here, you got better at the task. You're a little bit faster. Okay, here's the people who got active TMS. They got a little bit faster. Right? No effect of sleep deprivation. There was no slowing. You do see the slowing with people that got sham TMS. So that's normally what happens. Same with lapsing. You got very, very few, if any, lapses when you had active TMS. Okay, here's the normal kind of lapsing you see with the sham TMS. So we were able to get rid of the main effects of sleep deprivation in this task with our CPAS type paradigm. And this is something that was occurring a full day after the last TMS. Okay, so this is a long-lasting effect. I don't know how long it would have lasted because we let the people go to sleep, but we're able to actually create a kind of a virtual deficit in people, all right, that we were able to remediate. And we sold that to the NIA. They said everybody that's 70 years old or more has a working memory deficit, not just people with dementia. And we were able to show that with that stimulation to LOC again, you again speeded elderly people up. They're slower to begin with than, say, a young group like here. And both groups got faster at the task. When we stimulated this area, which also has to do, we showed functionally, has to do with the task, during the retention period, we made everybody worse, young and old, much worse. What we found out was that area is very much involved with rehearsal. So you're rehearsing these letters during the retention period, and we were interfering that with the TMS. When we brought the people back and moved the TMS to right before the task started, and the young people all got more accurate, which is this one. They're more accurate between active and sham, and faster. Okay. This is the accuracy. That's the reaction time. The young people got more accurate and faster just when we did the TMS. According to the ways that we know that works. The elderly got a little bit better, but they were still worse. So we're still working on that. In fact, we are working on that. Down at Duke, we got an R01 to do this and to use working memory training on people, which may or may not work, but with the TMS, it might work. If you can stimulate exactly the right area, say a dorsal alveolar prefrontal cortex, for the 2-week period that they're also doing their working memory training. And we're hoping that when we do that, people will be better in their working memory, elderly people, and it will transfer to other executive function. But that's ongoing, and we don't have any. I know that it's working so far. We're able to actually affect, so far, young people, 30 young people. We're making them all better at the task, and now we're starting to run older people. And just by the way, in depression, we tried this where we gave people therapy at the same time as they were getting the standard label, FDA label, TMS. And we did an open label study just to see if you could do that. And we were able to target it in people by having a task that's related to depression, okay? And I can't go into it right now, and I hope Holly will when she gives her talk, but it's related to depression. So we actually had a target. They don't have a target right now for depression with TMS treatment, but we think we found the target. So we were able on an individual basis have a target, and we gave them TMS in our CPAS form, during, with therapy during stimulation. We ran 5 people this way. It's an open label. They all got better. They all remediated, okay? And so we are in the process of setting up another study here where we do, a clinical trial of active versus sham with this to see if we can really more dramatically improve what TMS can do in depression. But again, it's about using this very specific kind of paradigm that we're calling CPAS, which that's what I'm saying there. So anyway, that's it. I'm only 5 minutes late. Does anybody have any questions or anything? It was so clear. Good. Okay, well, thank you.